We're going to spend some time reviewing acids and bases. You know acids and bases is a very extensive unit. So we're just going to go over a few specific points. Again, this document is in your review tab. I highly, highly, highly recommend that you print it out and look through it in getting ready for any type of weekend assignment, any type of practice test, and your real deal in May. The formulas for pH are given there, and really you do have a good smorgasbord of formulas given to you on your review sheet, on your reference sheet. You want to be familiar with what you have right in front of you. In regard to your acids and bases, you're looking here, and Henderson-Hasselbeck is given as well, at least if you have a weak acid. If you have a weak base, you'll have to make the adjustments to it. But be familiar with that as well. And again, you have this in your review tab. You know how to write Kas and Kbs. Remember, with Ka, you're going to generate hydronium ion or proton. With Kbs, you've got to generate hydroxide ions. With your salts, this was something that I asked you recently on a mini quiz, or on that quiz, and a lot of you guessed correctly in regard to where the pH range would be, but you weren't able to explain it. So let's take a minute to break this up for a sec. In the examples given here, what we've got ammonium chloride is a salt. Sodium sulfite, a salt. Potassium chloride, a salt. Yet these salts all have very different pHs. Two ways to approach this. In a multiple choice situation, I'd keep it simple. I would say, oh, ammonium hydroxide is a weak base. Hydrochloric acid is a strong acid. Strong beats weak, so your salt will be acidic with a pH less than 7. However, in a part 2 situation, you want to indicate what hydrolyzes. Group 1 ions do not hydrolyze. If you have the conjugate base that originates from a strong acid, that's not going to hydrolyze either. What hydrolyzes here is the ammonium ion. You would react it with water. It's going to generate ammonia and hydronium ion, and as a result you generate hydronium ion, hence the acidic salt. Again, in a part 1, you've got the strong base. Sulfurous acid is a weak acid. Strong is going to conquer weak, so this is going to be a basic salt with a pH greater than 7. Group 1 ions do not hydrolyze. You've got a sulfate ion, you will hydrolyze it, and you will generate the following: the generation of hydroxide ion, again a basic salt. So in a part 2 situation, you have to indicate which ion hydrolyzes. Why would potassium chloride be a neutral salt?
Strong base, strong acid.
Exactly. Neither ion's going to hydrolyze. You've got potassium hydroxide, a strong base, hydrochloric acid, strong acid, and so this one is going to have a pH of 7. Now, if you have weak, what do? You look at, think back to the lab you did, pre-lab number 3. Think back to lab 3, 4, which was on selecting indicators. If you have a weak, you look at their Ka-N, Kb, and whatever's greater will tell you if it's acidic or basic. Is that a little bit clearer? Because that was on a previous quiz and it didn't go well. All right. In regard to Henderson-Hasselbalch, this is an equation that is given to you. Right here. Percent dissociation is not given to you, yet it's asked very often. This is the amount dissociated. So this is going to be concentration of proton or hydroxide ion at equilibrium over the initial concentration of acid or base times 100. Be careful there. You know what Bronsted-Lowry conjugate pairs are, for example, the base and its conjugate acid or the acid and its conjugate base. So for example, if I gave you let's say this reaction, is that balanced for charge? We've got 1 minus on the left and we have 1 minus on the right. So yes, it is. Identify one conjugate acid base pair. You could pick this end, this, or you could pick this end, this. Doesn't matter what the acid or base is, it's just a pair. I've seen that asked. Easy point, can't be missed. Make sure you know your H-strong acids. 3 of them are binary, hydrochloric, hydroiodic, hydrobromic. Know the 5 ternaries, sulfuric, nitric, chloric, perchloric, periodic. You know that a strong acid ionizes completely such that the concentration of the acid is equal to the concentration of proton, provided that you have a monoprotic acid. A weak acid does not ionize completely. It ionizes very little, such that proton concentration is significantly less than the weak acid. And that's why with a strong acid you can get pH from the concentration directly. But with a weak acid you need a Rice table because you have to figure out the concentration of proton, which will be significantly less than the acid. In regard to acid strength, binary acid strength increases down a group. That's due to the larger radius. And it increases across a period due to increasing electronegativity. With ternary acids or oxyacids, what's going to happen there is going to decrease down a group due to the decreasing electronegativity. So the reasoning differs there. Be careful. They can also ask that. On a recent practice quiz, I believe, remember, the larger the Ka, the stronger the acid. That is an important concept too. So be careful there. You saw that on a recent AP exam. And it was this one. If you were given Ka values right away, which acid has to be stronger? Has to be this one, because it has a larger Ka. Remember, if you're drawing them, the H has to go to the O. That is critical as well. A lot of mistakes made there. And here's where your trends come in. If they threw this one in as well and you were comparing it to what you selected, what you're looking at here is the OH bond. We can diagram that out. Let's say, for example, you were comparing these two, and we had previously compared these two and we had indicated that this was stronger than this because the Ka was greater. So it appears as you're going down the periodic table with the ternaries, we're getting a decrease in acid strength. So if that's the case, which acid would you predict is stronger? This one or this one? Think about your periodic table. You have fluorine, chlorine, bromine, and iodine. So you would predict this one is stronger. So what are we seeing here in regard to the ternaries? If you consider what we stated previously, the acid strength is going to decrease, and that's due to electronegativity. And what do you know about the electronegativity of chlorine versus iodine? This has greater electronegativity. Again, fluorine has the greatest, so electronegativity decreases down a group, which we talked about maybe half an hour ago. And what you're seeing here then is that this has lower electronegativity. So this doesn't pull those electrons in the bond toward it as much, and that's not going to weaken this bond as much, whereas this bond will be a little bit weaker, hence the stronger the acid, and that's what it's looking for there.
But it's the opposite if there's no oxygen.
Right, if it's binary it is different, but if it's binary it's based on radius. So the larger the radius, the atoms can't get as close together, and so the bond snaps more easily. So if you're considering, for example, hydrochloric versus hydroiodic, iodine has a larger radius than chlorine, because iodine's valence electrons are in the 5th shell, farther from the nucleus with more electron shielding than chlorine's. So with the larger radius now, this bond is longer, hence it's weaker, it snaps more easily. So if you're considering acid strength for binary, it's this way. Okay? Couple things to remember. And again, if you take the review I gave you and you really put some effort into it, there's a lot of stuff you can pull up. A few more things I want to mention off the review, and then I've pulled up an old question that we can start to dissect. You may need to complete it at home as lunch is a little bit limiting. All right. Back to your sheet, I just wanted to mention amphoteric has the ability to act as both an acid or a base. You see it, for example, with this substance can act as an acid, that is, it can donate its proton, or it can act as a base accepting a proton. You see it with ammonia, you see it with water, etc. I don't think that'll be terribly critical. Except to say that you can get successive ionizations with the polyprotics. Shown here are a few graphs. Right away, looking at this first graph, let me blow it up a little bit so you can see.
Wait, can hydrogen phosphate ion also act as amphoteric?
Mono or di?
Mono.
Yes, can go either way. Looking at this first graph here, let me try and, I can't really hide this. Oh well. Looking at this first graph here, focusing on the equivalence point of 7, pH of 7 at the equivalence point, that has to be a titration of what? Strong acid is what you're starting with it, and you're adding strong base. Looking at this one now, you can see you're starting with weak acid, and you are adding strong base. The equivalence point is going to be greater than 7 here. This would be a weak acid. I'm sorry, you're starting with a weak base to which you are adding strong acid. And would this be a mono or diprotic acid? Di, you'd have 2 equivalence points here and here. You always want to find the midpoint. Going back to this one for a minute, let's say we're focusing on this blue line. What volume of base have you added at the equivalence point? 50. So at the half equivalence point, you would have added 25. And at the half equivalence point, what do you know about the pH? It's equal to the pKa. So these are all things you want to be comfortable with. And I believe it says that here, be very comfortable with calculating pH at any point on the graph, but also using the graphs to interpret concentrations. We'll mention that in a sec. You have to be able to figure out indicators that you can use. For example, if pH at the equivalence point is 9, you want an indicator that surrounds that 9 range, similar to the pre-lab that you did previously. And here were a few things that we mentioned as well. I just want to open this up for a sec because I think it would be extremely helpful to you. I know I had inserted this in your notes, and this came right here. This is something we had gone over previously and you've seen recently, but can't emphasize enough the importance of it. Here's a weak acid being titrated with a strong base. You're starting at a pH of about 2 and change. Here's where you have that weak acid. You haven't added any base yet, so you don't have any conjugate base because you haven't added any strong base. At this point, Let's go here for a sec. Here's your equivalence point. pH is 8, 40 mils of base added. What would be the volume of base at the half equivalence point? 20. And at the half equivalence point marked with the S, you know pKa is equal to pH, concentration of weak acid, and conjugate base is the same because you've neutralized half the weak acid, as we mentioned in the previous class going over that exam. Before the half equivalence point, you're going to have more weak acid than conjugate. Afterward, you're going to have more conjugate than you do weak acid. And when you pass the equivalence point, you'll have an excess of whatever it is that you added. So also a couple of key points. With that said, I had... I don't know. I think because I have so many of them. I thought that this question would be good. It's an older question, but it makes you think. Let's see if we can't work through a couple of critical pieces here. This is an older question, so the timing, the format, a little bit different, but not too bad. It says, each of the 3 beakers contains 25 mils of either 0.1 molar hydrochloric, 0.1 molar ammonia, 0.1 molar ammonium chloride. Determine the pH of the solution in beaker 1. What do we do? What kind of acid is HCl? Strong acid. So pH is equal to? Negative log of the proton concentration. What's the proton concentration? 0.1. What's the negative log of 0.1? 1 times 10 to the negative 1, so the negative log of that is 1. That's it. In beaker 2, the reaction of ammonia plus water yields ammonium ion and hydroxide ion. The value of the Kb for ammonia is this. Try and do 1 and 2 there, little 1 and little 2. Give it a shot. Try it. You'll be surprised just how many points you can pick up. And this is a question from the 2011 exam. It's the very first question. If you want more practice with acid and base, what's nice is on the old exams, the first question was always acid and base, KSP or KEQ. So there's a large number of questions out there.
Why did so many people get a 5 in 2015?
No, it was a change year. It's the last year of the old exam. It was heavily curved. Come on, let's concentrate. You finished already? I think I pulled up the scoring things too, otherwise I'll grab them. Here they are. Alright, so we had that one. Here's your KB expression, no sloppiness, right? Did you get that? Remember to take the square root. Now if they ask for the pH, what do you have to get first?
Concentration of hydroxide or proton.
I actually would go after the POH and subtract it from 14. I think it's easier. So the POH there would be 2 and change, so your pH would be 11 and change, right? Yes, yes? Did you get it? Yes? All right. Now it says in beaker 3, so that's this one, we've got ammonium ion plus water yielding ammonia and hydronium ion. Calculate the value for Ka. Well, that's very easy, because what did they give you that will lead to that? They gave you Kb, right? So how do you go from Kb to Ka? Kw. So Kw is equal to Ka times Kb. That's a formula that's given. Get the Ka. What'd you get? What'd you get? What'd you get? 5.6 times 10 to the negative 10 is correct. All right, now it's going to get messy. It says the contents of beaker 2, so you're going to pour the ammonia into beaker 3, the ammonium chloride. So what do you think you're making there? Starts with a B. A buffer, right? So you have ammonia, and you're going to mix it with the ammonium chloride, and essentially you are interested in that, right? And that's a buffer, correct? Because now if you throw proton in, that can react with that. If you throw hydroxide ion in, that'll react with that. So it will resist marked changes in pH if you add strong acid or strong base. So that was the goal of it. It says the contents of beaker 2 are poured into beaker 3 and you mix it up. Assume the volumes are additive. You started with 25 mils of each, so your total volume is 50. Calculate the pH. Initial concentrations were all 0.1 molar. What do we do? Give it a shot. Well, beaker 2 looks like this. And we established the KB. And then beaker 3 actually this KB was given, I apologize. This is the KA. Sorry. All right, so here, this KB was given, correct? Yeah, the KB here is 1.8 times 10 to the negative 5. And this KA we established at 5.6 times 10 to the negative 10. All right. Do we have to change this, or do we just have both of these substances present?
Don't we originally only have H4 and then mix it into the adding portion?
The add and the take away is typically when you add strong something. So in this case, you're just going to have amounts of these to get started. You've got a buffer solution. So I'd go off this with, you have initial amounts here of both. So you're going to have this, you're going to have this, you're looking for this, you've got a KA.
Could you put the screen, the test screen back up?
Just be careful, you have it, but you've changed your volume. So do it in millimoles and then get it to concentration. That's what I got right there. It is. Look. I didn't know if they had better work than I did. I just did it off that. So we had 25 mils of 0.1, so you had 2.5 millimoles of each one. You actually didn't have to follow it. They cancel each other, so pH is equal to hydronium here. Guys, 2011, it goes into more and more buffer stuff. You may want to take a look. If you don't understand, show me what you've got. We can look at it together.